Okay, so I think I'm going to get started. Hi, my name is Sam Rubenstein. I'm a hacker and a senior security analyst at the Security Threat Analysis and Reverse Engineering Center in Israel. We generally perform security evaluations of Cisco and third-party products, as well as evaluations for external customers. We mostly evaluate the security of embedded systems using a black box model, and we don't usually have access to source code, so we're particularly interested in all kinds of tools and utilities that are focused on binary analysis. So what exactly is this Frida thing anyway? The best way to get a feeling for what Frida is to see it in action. So let's start off with a quick demo just to give you a taste of how awesome Frida is. Okay, increase that. What we'll do is, I've got the Twitter app running here on my desktop, okay? What I'll do is I will use Frida trace to attach to the Twitter app, okay? And I'm interested in all functions that start with the word open, okay? It will tell me that it's auto-generating a whole bunch of handlers, okay? And that it started tracing 27 functions here at the end, okay? If we go to the Twitter app and pull down to refresh the timeline, we see a whole bunch of calls to open printed here, each in a different color for each thread. Each thread has its own color, so you can easily see when the opens are being called and from which thread they're being called. Okay. Now that doesn't really give us any useful information. It just tells us that the process called open, but we don't know what it actually opens. So let's see what we can find out about that. We saw that Frida generated a folder called handlers, okay? And in that folder, there's a subdirectory for each library which we've instrumented. And if we look at, for example, the libsystem.bdylib, okay, we'll see a whole bunch of different JS files, one for each of the functions which we have traced. If we edit the open.js function, we'll see that we have here a file which is JavaScript, okay? It has two main functions, onEnter and onLeave, okay? OnEnter receives a log, the args array, and some states, and onLeave receives the log and the return value, and then some states. What essentially happens is that when Frida sees that the application is trying to call open, it will first call our onEnter function over here, so we can log that open is being called and we can see have access to the arguments. Then the original function is executed, okay? And then the onLeave handler is called. If we come in here and say we want the first argument, okay, because that's the file name of that's being opened, so we can say arg0 and we can save, and we can come back to our trace, and we don't have to restart the trace because Frida automatically picks up the handler changes behind the scenes. If we pull down, we now get the pointers in the open function calls. The pointer isn't really very useful because we can't really understand what that is, okay? So what we want to do is we want to read the memory at the pointer location. And we have the Frida API memory.read UTF-8 string, which will read a UTF-8 string from the pointer in arg0, okay, and convert it to a JavaScript string. If we save again and then pull down, we now see the file name for each open call. That immediately gives us some information about what's going on in the application. For example, we can see that they're using Crashlytics for crash reporting and error reporting. We can see that they store the profile images for all accounts that are being watched in your timeline, things like that. It immediately gives us more information about how the application processes. And you can see that we can easily write JavaScript code in the handlers to perform very complex actions, things that would be difficult to do even in debuggers. So Frida is an in-process binary instrumentation framework. It's a framework which allows you to run code within the context of a target binary application in order to instrument, inspect, analyze, and potentially modify the behavior of that process. You can think of it like a sort of grease monkey for native applications. In fact, grease monkey is a great analogy because the instrumentation code in Frida is written in JavaScript. The JavaScript code runs within the context of the target process, so it has full access to all the process resources, including memory, file descriptors, sockets, etc. Having the instrumentation code in JavaScript lets us eliminate the compile, reload, retry cycle that you'd normally need when using other tools or techniques like LB preload. You can just make your changes to the JavaScript handlers, and they're immediately reflected in Frida. Frida is multi-platform, multi-arc. It lets you instrument processes on all of the major platforms and architectures. Because there is the in-process code, which actually interacts with the target, is in JavaScript, you can build tools which use the same instrumentation scripts on multiple different target platforms or architectures. When we started looking at Frida, we noticed that it didn't have support for the QNX system. So I don't know how many people are actually familiar with QNX. Does anybody know QNX here? So one person or two people. Okay. So QNX, or more accurately, QNX Neutrino, is a commercial real-time microkernel operating system, which is very widely used in embedded applications. QNX Neutrino runs on a variety of different hardware architectures, including x86, PowerPC, ARM, MIPS, and SH4. QNX was purchased in 2010 by Research in Motion, RIM, and is used as the operating system on newer BlackBerry smartphones and the BlackBerry Playbook tablets. Neutrino was designed from the ground up to be fully POSIX compliant. This makes it relatively easy to port code written for other Unix-like operating systems to the QNX environment. QNX provided GCC-based toolchain, which can be used to build software targeting their platform. This allows for broad compatibility with existing software packages. QNX also reuses the ELF executable file format made popular by the Linux and BSD platforms. There is no native GDB which runs on QNX. Instead, they have a process they call QCon, which acts as a GDB server and lets you connect from a GDB on a development host and debug processes running on QNX. QNX Neutrino is very commonly used as the operating system for automotive electronic control units, such as infotainment devices found in modern cars. We at Ster have spent the last few years performing evaluations of electronic control units for a number of the big automotive vendors. And we've seen that a number of these ECUs run QNX OS, usually on ARM hardware. So we thought it would be really awesome to be able to use Frida on our QNX ARM targets, as it would aid us by allowing for easy advanced dynamic analysis of processes running on those targets to complement the static analysis that we routinely do on those targets. Before we discuss some issues that we encountered when porting Frida to QNX, let's take a brief look behind the scenes to see how Frida actually works. We said that Frida works as an in-process analysis tool, in-process debugger. With Frida, your JavaScript instrumentation code runs in process. This means that we need to inject your code into the target process. The code that is injected is a dynamic library called Frida Agent. This agent includes everything that is needed to run your JavaScript instrumentation code in the target process. It includes a full JavaScript engine, which is used to run the instrumentation scripts themselves. It implements the functionality required to perform function interception, function hooking, and function replacement. It includes code to interact with the process's resources, such as loaded modules, memory, sockets, and file descriptors. And it also includes a communication mechanism which allows Frida-based tools running on your development host and your user's host machine to load scripts into the process and interact with them while they're running in that process. Frida includes a component called Frida Server, which runs on the target device and listens for connections from Frida-based tools running on the user's host. It implements the functionality required to attach to a target process and inject and run the Frida agent library inside that process. I think a diagram will help to clarify the roles of the different components and their interactions. So here we have a host machine and a target device. The target device also has a target process running on that device. Note that the host and the target might be at the same machine. The first thing that happens is that we ensure that Frida Server is running on the target device. Next, we run our Frida-based tool on the host, asking it to attach to the target process. So the Frida tool will then connect to the Frida server on the target and ask it to attach to the process with a specified PID or name. Frida server then injects the Frida agent into the target process, creates a new thread, and executes the agent's main function on that new thread. The Frida agent loads the JavaScript engine and creates a communication channel that can be used by the Frida tool on the host. The Frida tool then asks the Frida agent to load and execute a JavaScript instrumentation script. This script then performs the desired analysis or instrumentation. Porting Frida to a new platform doesn't require all that much code, as Frida is well designed and modular, with the platform-specific code limited to just those bits which are actually platform-specific. Those parts which it is necessary to implement are really low-level platform code, low-level system programming, and it requires you to dig into the guts of the target platform to work out how to do stuff on that platform. Because we're working at such a low level and we're dealing with peculiarities and the details of target platforms, we encounter the most exotic bugs. You get really, really strange bugs in Frida when porting, as opposed to simple bugs that you'll see in your everyday software. You get really interesting and peculiar bugs, some of which we'll describe later. Because QNX is POSIX compliant, uses a GCC toolchain, and otherwise feels very Linux-like, it's easy to assume that porting Frida to QNX would be a simple matter of copying the Linux support and using that code. Frida on Linux uses the procfs file system to retrieve information about the systems and processes. Among other things, it uses procfs when it's enumerating the processes running on the system and when listing the modules and memory ranges loaded into a particular process via the procpid maps pseudo file. Unfortunately, QNX does not provide the same kind of information via the procfs file system. It has a completely different procfs implementation to the Linux or BSD procfs that we're used to. On QNX, there is only a single file available for each process under the procfs. This AS file exposes the address space of the process, allowing for arbitrary reads and writes to the process's virtual address space. Obviously, if you have a user which has the permissions to access that process, so you have to have the same user or high privileges. In addition to reading and writing process memory through the AS file, you can also perform other actions on the file using the devctl mechanism. devctl is very similar to ioctl that you'll see on normal Unix-like machines. It allows one to send device-specific commands to a given file descriptor. On QNX, the procfs implements a number of useful devctl commands which allow us to perform actions such as listing the modules loaded in a process or getting and setting the registers for a given thread in the process. We'll see how those are used a little bit later. In fact, QNX uses the procas and devctl mechanisms to implement the QCon debugger that we talked about earlier and provide debugging functionality on QNX. So all of the debugging is actually done via this procfs implementation. We can use these same mechanisms that are used by the debugger on QNX to implement the necessary process inspection functionality that we need in order to get Frida working. One of the most important platform-specific parts of Frida is the injector. The injector is responsible for injecting the Frida agent shared library into the target process and executing its main function on a new thread. The injector is part of the Frida server component that we described earlier. Now, QNX does have a thread create function, which is similar to the create remote thread function that you might know from Windows. It's supposed to allow one to create a thread in a remote target process. So this would be ideal to be able to use this function to implement injection in QNX. But if you dig into the details a little bit more, you find that only one process, which is called the process manager, which is a particular system process. You can think of it as the init process in Linux, PID1. Only that particular process is allowed to create threads in other processes. So we have to find another way to achieve our goal of creating a thread and running our code in the target application. On Linux, we don't have create remote thread either. And there, Frida uses a technique called thread hijacking to create a remote function call primitive. The remote function call primitive allows one to execute a function in the remote target process. We can use this primitive to call mmap or to allocate memory in the target process, or use pthread create to create a new thread within that process. This is done by first attaching to the process using ptrace attach. This has the effect of pausing or suspending the target process and gives us a handle to it. We then retrieve and save the registers for the main thread. Then we set up the call by setting the PC in the thread's register set to the address of the function that we're interested in calling. So it might be the address of mmap or pthread create. Obviously, we have to resolve those addresses inside the targets by finding the correct library and using the correct offsets from that base of library. Then we set up the registers and we write argument values into the target thread stack in order to specify the arguments for the function. We can use pthread poke data to write data into the stack of the target thread. Then what we do is we set the return address to be some dummy value, which will cause a seg fault when execution tries to branch to it. We'll wait for and catch this particular seg fault in order to know when our function is completed running. We then set the registers on the process's main thread to our modified values, and we use ptrace cont to continue the process, which will have the effect of it executing the target function inside the process. We wait for the seg fault that indicates that it tried to branch to the dummy return address, and that way we know that our target function is completed running. So using this technique, we can inject a call to mmap or inject a call to pthread create into our target process. Once we've finished running our target function, we can restore the process to its original state by simply resetting the registers to the original saved values, thereby letting the process continue exactly where it was before we started the hijack process. So this can be thought of in general as similar to a context switch, in that you have the CPU changing from running one thread to running the code for a different thread, except that we basically forcing a thread in a target process to context switch to running our target function. So this technique seems simple enough. Let's try to port it to QNX. Of course, it turns out there's no ptrace on QNX, right? So we can't just port it directly. But fortunately, the QNX procfs does implement most of the required functionality via the devctl mechanism. We can issue the dcmd proc stop devctl to stop the target process. We can then use dcmd proc get greg to retrieve the target thread's registers. We set up the call exactly how we did it for using ptrace. The only difference is instead of using ptrace poke data, to set up the arguments on the stack, we need to write the process's address space using the proc PID-AES file. We then can use dcmd proc set greg to set the target thread's registers for the call, and we can resume the resume the target application using dcmd proc run. It will continue the process, having it execute our target function. We again wait for the execution to cause a fault when it attempts to access the dummy return address. Then we can resume the original operation of the target by restoring the original register's saved values. Using this thread hijacking technique, we are able to perform the remote calls necessary to implement the injector mechanism. So using this technique, we're actually able to fully implement the injector of QNX, of Frida for QNX. Frida makes heavy use of code modification. For example, to implement inline function hooking for interception, Frida overwrites the initial bytes of the target function with a trampoline or jump to a trampoline to the interception code. For example, if we have this function prologue, Frida will overwrite the first 3 instructions with a jump to a trampoline. This trampoline will then call the JavaScript on enter function, execute the original function code, and call the JavaScript on leave function. Because ARM is a modified Harvard architecture, it has separate instruction and data caches. In order to have modified code execute correctly, we need to make sure to clear the instruction cache after that code has been modified. Otherwise, it will try to execute garbage data. GCC has a built-in function called clear cache, which is intended to do exactly what we want. It clears the instruction cache on platforms that require such. This is the disassembly of the implementation of the clear cache built-in function from the QNX ARM libgcc.a. Okay, this is the implementation of the clear cache built-in. At first glance, this looks okay. The function simply calls the QNX specific msync function and asks it to invalidate the region passed in R1 and R0. But when we try to actually use this function, things go horribly wrong. And it turns out there's a really subtle bug in this code. Well, subtle maybe bug. I don't know, you guys can tell me if it's subtle. This instruction, the BL, implements the call to msync. BL is branch with link, and it's the equivalent of the call instruction on x86. What it does is it will set the link register, LR, to the address after the call, which is offset C in our code here. And then it will call the target function. When the msync function is finished executing, it will branch to the link register we have just set, return it to the clear cache function after the call. We then want to return to the caller of the clear cache function itself. So we want to do a branch with exchange to the link register. But here's the problem. We just set the link register to the offset 0xC in the previous instruction. So what will actually happen is it will branch back to the same BXLR, and we'll keep doing that infinitely because LR has been set to 0xC here. The bug is that the clear cache function did not save the original link register before it used a branch with link operation which modifies the link register. So this is just a bug. Someone was tasked with coding the clear cache function, and it has to be done in assembly for some reason, and they just screwed up the assembly so that this function cannot work. So they didn't even bother to test it. Okay? We work around this bug in QNX by simply calling the msync function directly in Frida. We also mentioned earlier that one of the things that's included in the Frida agent is a full JavaScript engine. Originally, Frida used Google's V8 JavaScript engine, which is written in C++. And when we started to intercept some functions on QNX, we started to get these fairly randomized seg faults that were faulting in the V8 code. So we spent a whole bunch of time in trying to understand what was going on. And V8 code is, I don't know if you've ever looked at the V8 code, but it's C++ and it's ugly and it's big and there's a lot of very C++y type paradigm stuff that you see, the scoped variables which automatically clean up after themselves and all kinds of things like that. So after we spent time debugging the V8 code, we actually determined that the issue was that we were running out of stack space. It turns out that on QNX, the default max stack size is just 128 kilobytes, which is tiny. Linux, for example, has a default max stack size of 8 megabytes. 128K is just not enough to actually run the V8 engine. So how can we resolve this? Because we need the V8 engine to run, and we need our JavaScript instrumentation functions to run. So what we can do is we can intercept pthread creates and make sure that all the new threads that are allocated in the function in the process are allocated with some reasonable max stack size. This works for new threads, but what about existing ones? We injected into a process that was already running. It had 10 threads running. How can we deal with those threads? The V8 engine has to be able to run on those existing threads because you want your instrumentation scripts to be running in the same thread as the functions that are being hooked. So what do we do about these existing threads? It turns out that there is just no way to modify the max stack size of an existing thread, either in QNX or in Linux. You just can't do this. It's something that was never thought to be required. How do we resolve this issue? What we ended up doing is that we allocated 2 megabytes on our own for each thread. And what we did was we used it as a side stack. When we came into interception code and we wanted to start running our JavaScript code, we would switch the ESP from, or the SP in ARM, we would switch the stack pointer from the real stack to a buffer that we allocated per thread of 2 megabytes. Okay? And we just use that stack for the execution of the interception code and the function itself. This gives V8 enough room to breathe so it actually works, but it's a horrible hack. We ended up allocating a lot more memory than we actually need because we don't have the lazy allocation mechanism that you have in the stack. So we actually allocated 2 megabytes per thread ahead of time. And there are also a whole bunch of different edge cases and strange scenarios where things might go haywire. One of the interesting scenarios is what do you do about stack arguments? So you have to copy part of the original stack. How much do you copy? So we said, okay, we'll copy 1 page, and we assume that you haven't got arguments greater than 1 page. But that's a hack, and it can go horribly wrong in all kinds of interesting ways. The truth is that V8 is just an incredible resource hog. It was designed to be running in browsers on PCs. It wasn't intended for use in embedded applications at all. Just to give you some basic feel, the V8 engine itself, when compiled, takes up to 6 or to 8 megabytes of space in memory and on disk. Okay, so you're adding 6 to 8 megabytes to your application just for the V8 engine itself. Additionally, the C++ requirements might be difficult to satisfy on some platforms. Because V8 is such a pain on embedded systems, we actually went ahead and ported Frida to use a completely different JavaScript engine, which is called duct tape. Duct tape is a tiny single C-file JavaScript engine, which is easy to integrate into applications. It was designed to be portable and to run on embedded and constrained systems. So it was designed from the start for embedded and constrained systems. Once we ported Frida to duct tape, we no longer need the side stack, as duct tape runs just fine with 128K of stack. Performance-wise, the duct tape runtime is comparable to the V8 runtime. It comes to about 1 millisecond of overhead per function hooked. And in fact, in some cases, we managed to get duct tape to actually beat V8 performance-wise. Duct tape is now the default JavaScript engine for Frida on iOS, QNX, and Linux ARM. There are only 2 features that V8 has that duct tape doesn't. The first is a JIT. V8 will perform much better on large instrumentation scripts, as the JavaScript code is just-in-time compiled to native code, which then runs directly on the CPU instead of being interpreted by the JavaScript engine. In fact, the way that you select the duct tape runtime on desktop Frida is to add the disable JIT command line argument. V8 is also compatible with the latest and greatest ECMA script 6 standard, which includes the most up-to-date JavaScript functionality. Duct tape only supports ES5 and a few of the ES6 features, so you might need to translate your instrumentation scripts if you used ES6 features. You might need to translate that to ES5 for use with duct tape. The next issue we encountered was to do with sig set jump, sig log jump. Show of hands, how many people have familiarity with sig set jump and sig log jump? Okay, again, about 3 or 4 people. So I'm going to explain them anyway. Sig set jump and sig log jump are functions which are used for dealing with errors and interrupts, which are useful for dealing with errors and interrupts encountered in C code. Sig set jump saves the stack context and execution environments at the point it is called. A subsequent call to sig log jump with the same environment variable will restore the saved execution state to that state saved when you called sig set jump. The call to sig set jump returns 0 if it returned normally, i.e. you just called sig set jump, and it will return non-zero if you return to that point in execution because of a sig log jump. So you can distinguish between the case where you just called sig set jump to save the state and where the case when you called sig log jump to restore states to that particular location in the code. These functions allow one to implement a kind of poor man's exception handling in C. Frida uses sig set jump and sig log jump to implement exception handling so that, for example, attempts to access illegal addresses using the Frida APIs can be caught and handled instead of causing the target process to crash. So I'll explain it a little bit better with a little short demo, which will show how sig set jump and sig log jump can be used to implement simple exceptions in C. We have here the divide C file, which is just a really short example which shows sig set jump and sig log jump in action. What we have here is we have a main function. The main function registers a signal handler for the sig FPE, the floating point exception signal. And what it does is it just registers that when that signal occurs, it should call the onSignal function we have at the top here. Then we have a call to a sig set jump, which will save the environments in the env global variable, the execution environment and program state. If that sig set jump returns 0, we enter the try block, okay, where we have the int divisor is equal to the ATL of the argv, so you take the divisor from the arguments, and then you just have the printf of divisor and 100 divided by divisor. If we return to this line because of the sig log jump, then we'll enter the else, which is the catch phase of the execution, and we'll print an exception the division by 0 was encountered. Okay? If we compile that and then execute it with, let's say, 10, we get 100 divided by 10 is 10. But if we execute it with 0, we get a division by 0 detected. Okay? So you can see that using sig set jump and sig log jump, it's really easy to implement relatively simple exception handling in C. On QNX, sig set jump is defined as both a macro and a function. Why? I don't know exactly. By default, Frida tries to use the sig set jump function. However, it turns out that the sig set jump function is broken on QNX. The sig set jump function allocates some storage on the stack, which is used as part of the saved execution state. It then returns, thereby releasing the stack storage. But the saved execution state still refers to that released storage on the stack. This is like a function returning the address to a local variable on the stack. Okay, it's no longer valid after the function returns. Code in the try block of the sig set jump if then overwrites that stack storage as part of its normal function, corrupting that part of the saved execution state. If an exception occurs, we'll try to restore the execution state with sig long jump, but that state is now partially corrupted, resulting in a crash. This is a bug in the implementation of the sig set jump function on QNX. It should not use stack storage, which is normally used for function local variables, as part of the execution state it saves. The macro version of the sig set jump function allocates the stack storage in the stack frame of the callee. Sorry, not the callee, the caller of the calling function. And therefore, it's not released when the sig set jump macro returns. This means that the macro version of sig set jump works as expected. So if we force Frida to use the macro of sig set jump, it works correctly. So despite encountering some seriously exotic bugs, we managed to port Frida to QNX for ARM, and we've used it on a couple of our automotive targets with great success. Frida is really a very powerful tool which enables quick and easy advanced dynamic analysis. For those of you who didn't have a chance to participate in my workshop yesterday, there will be a talk at B-Sides on binary instrumentation with Frida, which you're welcome to attend. We can now update the Frida platform support matrix to include QNX ARM for Frida. Obviously, there are probably still bugs lurking in the QNX ports. We already know a few features that we haven't implemented, like process spawning, for example. We haven't yet implemented those on QNX. We'd be grateful for additional testing and pull requests. So if you do have QNX targets and you're interested in testing out Frida, please let me know. We'd be happy to help you get that running. One of the things we know we don't have is QNX support for x86. It's something that we would really round out the support for Frida for the platform, but we just didn't have any use case to implement it yet. But implementing it shouldn't be a huge deal because there is Linux x86 support, and most of the code is very similar. So we could easily implement x86 support if you have a test case, a use case for that. You can find more about Frida at the website, frida.re. The code is available on GitHub. If you have questions or issues, there are always people who are very happy to help you get started or work through any difficulties you might encounter in the IRC channel on Freenode. Feel free to hit us up there, ask questions about Frida. I think Frida is great, and I don't know if anybody who was in the lecture yesterday, I think people enjoyed it as well. It's really a powerful toolkit. That's all. Questions?
So you mentioned you're targeting QNX. Which versions of QNX are you targeting? Because ptrace does exist in later releases.
No, it still doesn't exist in 6.6. We targeted QNX 6.5, okay? And we targeted just the ARM. QNX 6.5 has support for two ARM ABIs, ARM standard ARM and ARM EABI. So we support both ARM and ARM EABI. On QNX 6.6, there's only ARM EABI. But so far as I know, there's no ptrace on QNX 6.5 or 6.6.
Because there is a GDB that works on QNX.
Yes, but the GDB doesn't use ptrace. It uses the debctl mechanism and.
Okay, that's where my misunderstanding.
Yeah, there is no ptrace. So
sure. And can you hook QNX messages? So rather than hooking at the POSIX level, so that you're catching libc type functions, can you hook QNX messages?
Talk about the pipe messages?
No, so essentially QNX will load a surface in terms of the microkernel architecture is essentially.
Oh, that's what you mean. So you could theoretically hook them by hooking the C functions that implement that functionality We haven't got any particular support for QNX messages as a runtime, but if that's something that you'd be interested in doing, it should be relatively easy to write in JavaScript using hooks of the C functions that are appropriate. Yeah. And I'm sure we'd be happy to see that. Anyone else? Okay. Thank you very much.